Hi Geo R, this is Unit 2, Lesson 7, and today we're going to talk about being congruent in terms of a rigid motion. So in exercise 1, I have square ABCD on the left, and I have rhombus GHIJ on the right. And you can see by the way that it's marked that all these sides are the same. So AB is the same as BC, CD, it's even the same as all of these over here. So the first question they're asking, are these figures congruent? Now to be congruent, all the sides have to be congruent, which they are, but also all the angles have to be congruent. So angle A is 90 degrees, but angle G, we don't know what it is, but it's not marked as being 90. So are these congruent? No. The sides are congruent, which is part of it, but the angles would also have to be congruent, and that is true. The sides are congruent, but not the angles. These are not the same shape. So they can't be congruent to each other. ABCD is a square and GHIJ is a rhombus. So here's our definition of congruent. To be congruent, figures are congruent if there's a rigid motion or motions that maps the pre-image onto the image. So figures are congruent if there is a rigid motion. Now I'm going to write motion and then I'm going to write parentheses S because there could be a more than one rigid motion. So if there's a rigid motion or motions that maps the pre-image onto the image. Okay, so now we're going to use that definition of being congruent. There has to be a rigid motion that maps one figure onto the other. We're going to use that to describe why the figures in exercise 1 up here are not congruent. So why is ABCD not congruent to GHIJ? Because there's no rigid motion that maps ABCD onto GHIJ. I can't reflect it, I can't rotate it, I can't translate it. There's nothing I could do that would make that square turn into a rhombus. All right, that would change the angles. Because remember, to be a rigid motion, it preserves the length and the angle measure. All right, exercise 3. In the figure below, the triangle on the left has been mapped to the one on the right by a rotation of 240 degrees about point P. Identify all 6 pairs of corresponding parts, angles, and sides. So basically, just so you can maybe visually see this a little bit better, I'm going to connect A to P, and A corresponds right here to X. I'm going to connect that to P also. Now I did a rotation of 240 degrees. Remember, all my rotations are always going to be counterclockwise. So I rotated it 240 degrees about point P. So angle A maps to angle X, angle B maps to angle Y, and angle C maps to angle Z. Therefore, side AB maps to side XY, side AC maps to XZ, and BC maps to YZ. Is triangle ABC congruent to triangle XYZ? Yes. Remember our definition, to be congruent, there has to be a rigid motion. So yes, there is a rigid motion. The rigid motion that we used was a rotation of 240 degrees, but there's a rigid motion that maps the pre-image to the image. What rigid motion maps ABC onto XYZ? And we're going to write this in our composition form here. And just move this up a bit. So basically, I did a rotation about point P. You always want to say what you're rotating it about, and then you put the number of degrees that I rotated it. So I did a rotation about point P of 240 degrees. And I took triangle ABC, and that image was triangle XYZ. All right, let's just talk about rigid motions again. Rigid motions produce congruent figures and therefore congruent parts. So if you have a rigid motion, I'm going to get a congruent figure. So they produce congruent figures and therefore congruent parts. What do I mean by the parts? I mean the angles and the sides. You're going to see we're going to call this CPCTC when we do proofs in the next chapter. CPCTC means that the corresponding parts of congruent triangles are congruent. So basically, once the triangles are congruent, then the corresponding parts, all those angles and sides, also have to be congruent. All right, let's do one that's not actually congruent. So if we're looking at exercise 4, each side of XYZ is twice the length of ABC. Fill in the blanks below so that each relationship between the lengths of the sides is true. Meaning, like if I took AB, which is this side on the left, and multiply it by 2, I would get XY. If I took BC, which is the side on the bottom, and multiplied it by 2, I would get YZ. And if I took AC, which is the side on the right, and multiplied it by 2, I would get XZ. Are these triangles congruent? No, the length is not preserved in them. You can see that one is definitely bigger than the other. So length is not preserved. There's no rigid motion that maps ABC onto XYZ. I did a dilation, and we're going to talk about dilations in a separate chapter, but a dilation changes the size. A dilation is not a rigid motion. Okay, so there's no rigid motion. I made this bigger, and a dilation is not a rigid motion. So just because I have corresponding parts does not mean that those figures are going to be congruent to each other. All right. So in exercise 5, I have ABC, which is a triangle on top, and I'm telling you that it's congruent to DBC, which is the triangle on the bottom. Give a rigid motion that maps ABC onto DBC. Explain how the rigid motion does the mapping. So you can see that I basically just flipped this over this line right here. I took the triangle ABC and I reflected it over line BC. So the rigid motion, or the transformation, is I did a reflection over BC. Okay, so that's the rigid motion. And in that reflection, just so we can see what maps to what, B maps to B, because it's on the line of reflection. C maps to C, because they're on the line of reflection, and A maps to D. Okay. Six, in the diagram, TRS, which is a triangle right up here, is congruent to TUV. Give a rigid motion that maps TRS onto TUV. So I didn't reflect this, but what I did is I rotated it. Now, this is important also. The order of the letters tells you what maps to what. So see how R is this middle letter and U is this middle letter? So R maps to U. And how am I doing that? I'm doing a rotation about point T of 180 degrees would make triangle TRS map onto TUV. So the T would maps onto itself, it stays there, but R maps onto U and S maps onto V. And again, S was that last letter and V was that last letter. So the order of the letters tells us what maps onto what and can help us. And then my last one, I have a graph describe a sequence of rigid motions that would map ABC onto DEF. Explain why this shows that the triangles are congruent to each other. So you can see that A is that first letter and D is that second letter. So A maps onto D. A is on the left and D is on the right. So that means I must have done some sort of reflection. So let's reflect it over this y-axis. All right, so if I reflect it over the y-axis, remember that's the second thing that I'm doing. If I do that, then let me just count how far away. 1, 2, 3, 4, 1, 2, 3, 4. Here's my new C. A is 1, 2, 3, it's 8 away. 6, 7, 8. You can tell by, I made every 5 is a darker line, so just to make it easier to count, E is on that darker line, so E is 5 away. So this is my new image right here after I do the reflection. I want to draw that so then I can actually see what translation I need. So now that I have this in the right spot, I'm going to move it over 2 and up 1, 2, 3, 4, 5, 6. So I'm going to do a translation of -2, 6. So that's the sequence of rigid motions that would map ABC onto DEF. Why does this show that the triangles are congruent? Well, I did a reflection and a translation. A reflection and a translation are both rigid motions. Oops. A reflection and translation are both rigid motions. And the important thing that we're going to say is they preserve length and angle measure. Are both rigid motions. They preserve length and angle measure. That's the key word right there. Preserve length and angle measure. So the triangles are congruent. Reflection and translation are both rigid motions. That means that they preserve the length and the angle measure. Therefore, those triangles are going to be congruent to each other. Okay, we only have one more.